Okay, chapter 4, sections 1 and 2. Extreme values, Rolle's theorem, the mean value theorem. What questions do you have for me? Yes.
Can you go 22 and 4 point, or question 7?
4.122. So 22 says, sketch the graph, use the sketch to find absolute extremes. Do you want to do 21 or 23? All right, well, let's take a look at 23. So this function, we are given f of x is ln of x from 0 to 2. And it's important that I note here that we're not including 0. Okay. What's the graph of this function look like? I need at least at the base level an understanding what the graph of ln of x looks like, or I need my graphing device. Draw me a picture. Yes. Oh, absolutely. So this graph goes through the point 1, 0. And at the point 2, we hit a value of roughly 0.693. But as we get closer and closer to 0, what happens on this graph? Say again? It goes negative. And not only does it go negative, it keeps going negative. Because you can't put 0 into the ln. When you try and do ln of 0, your calculator goes, ln is only defined when the x is positive. That's why 0 is not included here. So this goes downward forever. Okay. Use the graph to find absolute extremes. Do we have an absolute maximum? There's the highest dot on this picture, right? Right here. Absolute maximum value is 0.693, the rest of the decimals. That's ln of 2. At x equals 2. If you wanted to, you could write it as a point. Is there a lowest point on this graph? Well, because this asymptote exists at 0, that means I can continue getting closer and closer and closer to x equals 0 and continue to go down. I know the limit as x approaches 0 from the right of ln of x is minus infinity. That means there isn't a lowest point, and that means there is no absolute minimum value. No matter how much closer I get, I can always find another step in and another step down. So what I really need to know in order to be able to solve problem 22, Fiona, is I need to know what that graph looks like. I need to know where its range of y values is. And then I need to say, okay, here's my maximum. And if there's more than one, these are tied. Here's my minimum. If there's more than one, these are tied.
So it's
There's no number down there, is there? That's the point. Infinity is an idea. It's not an actual number in this universe.
thank you.
So I can't do the Buzz Lightyear routine and go to infinity and beyond. I'll save that for another course because there is a way to do that. It's just not here. SMA 331 complex variables talks about that. More questions. Or I could just go wandering off onto my tangent. 4.2, number 30. So let's take a look at 29. I am told f of 1 is 10. I am asked, about f of 4. This is in 4.2, right?
Yeah.
So this is my mean value theorem, my Rolle's theorem idea. My first reaction is to at least half-assedly draw a picture. So I've got x going from 1 to 4, and I've got f of 1 being 10, right? F of 1 is 10. What you thinking? You grimaced and you looked at the screen and you waved your hand. Talk to me. What are you thinking?
How do we graph the problems?
I don't know what f of 4 is, right? But I do know that if I had a dot, I'd be able to say something about the slope between those two dots, right? The slope between those two dots would be f of 4 minus f of 1 over 4 minus 1. But I don't know what this number is. Correct? I know what this number is. And I can do the subtraction on the bottom. That slope is part of my mean value idea. So I'm thinking now about the mean value theorem. The mean value theorem tells me if I have a function that's continuous and differentiable, then what's the conclusion of the mean value theorem? There's my if statement. What's the then in the mean value theorem? Uh-oh. I don't know what the theorem says. I can't use it. Chase?
Is a value x equals c within f, the f prime of c.
F prime of C
Equals f of b minus f of a over b minus a.
Aha, that's exactly this expression, isn't it? So I now know if I have a function that's continuous and differentiable, then I can use this idea. The derivative somewhere is equal to this average rate of change, this mean value. Now, let's go back up to the statement of the problem. I'm told f prime is bigger than or equal to 2 from 1 to 4. That's a closed interval, right? And if a function has a derivative, then it's differentiable. And if a function is differentiable, it's continuous. This statement right here is enough for me to go down to the mean value theorem and say, check, check. The if works. That means the conclusion must be true. If P, then Q, hey, all of the things in P are true. Q must be. That means that I can now say, this is true. One less than or equal to C less than or equal to 4, because that's our interval. F prime of C equals f of 4 minus 10 over 3. You with me so far? Now, here's the sneaky part. We're asked about f prime of 4. I'm sorry, f of 4. So let's get f of 4 all along. Let's rearrange. Here's the magic part. how small can f of 4 be? I want to know a lower bound for f of 4. I want to be able to say f of 4 is less than or equal to something. But I know f of 4 is exactly equal to this. But I don't know what this number is, do I? What I do know is that that number is always bigger than or equal to 2, isn't it? This number is bigger than or equal to 2. F of 4 must be bigger than this. That's a lower bound, and that number is 16. Now, let me go back to the picture because you said I don't know how to draw this, right? So here's what I'm going to do. I'm going to say on this picture, I don't know very much about F, but I do know it goes up at a rate bigger than a rate of 2. So every time I move over, I'm going to go up 2. There's the line whose slope is 2, right? I'm sorry, it's kind of hard to read that I wrote those numbers on here. Let me write them darker. Yes? But F has to be, this is the line with slope 2, and F prime is bigger than that. The graph has to go up from here, doesn't it? So I don't know where this value is, but I know it can't be any smaller than this. That's my lower bound. You're welcome. There are a lot of places in math and computer science specifically where we aim to find lower bounds for things and upper bounds for things. I was actually just teaching this last week in the discrete math class, the next class in the math major series. And one of the things that I said is we use this to talk about how complicated something is to do. Let's suppose I gave you a list of papers in alphabetical order. And I asked you to find a last name that started with L. How would you do it? I promise this is not a stupid question. Sure sounds like it though. The names are in alphabetical order. How would you find a name that began, a last name that began L? Right? In order, you'd go to L. If I give you a list of numbers and say, find me 7,313 in this list that goes from 1 to 70 billion or something, and the numbers are not all in order, they're not all there. Maybe it's only, 100,000 numbers. Find me this one. This is a Google search. Find me this result. If you go in order, that's going to take a long time, isn't it? So if I could say, well, if you have this many things, it can take no more than looking through all of them. Is there a faster way to do it? If the things are in order, sure there is. I know where the L's are in the alphabet. I can go to the L's. If my numbers were in order, I could keep cutting the list in places where I knew things were in order, and I can do these things faster. We bound our complexity, how much time it takes to do something, in exactly this sort of way. That's called algorithmic complexity, and there is time complexity and space complexity for the speed of a computer algorithm and the amount of memory it takes. And that's why we keep building faster and faster computers. Anyhow, by the way, that's also a problem worth $1 million. There are algorithms that are so hard to do, so complicated to do, that we don't know how to solve them in a time less than the life of the universe 100,000 times over. If I asked you to visit all 48 state capitals of the United States by car, start here in Harrisburg and visit them all, find me the cheapest trip. The only efficient way to do that is brute force. Write them all out. If you wrote one a second, you would not be 1% of the way done in the life of the universe so far. That's a really hard problem. If there's a shortcut to it, if there's a way to make the algorithm bounded by something nicer, then we'll go from not tractable, not solvable problems to more solvable problems. In the year 2000, the Clay Math Institute came up with 7 different problems. They were called the Millennial Problems. They're known as the Millennium Prizes now because the Clay Math Institute put up $1 million a piece. If anyone can solve any of these problems, we'll give them $1 million. That complexity problem is one of them. 1 down, 6 to go, but it's not the complexity problem. One of them has been solved so far. Clay Institute, claymathinstitute.org, I believe. It's worth a look. Anyhow, so you can make money in math. More questions? Here's how you make infinity a number. I have a number line, right? Its horizontal axis is a number line. So I'm going to mark out 1, 2, 3, 4, -1, -2, and there's 0 right there. I've put the circle whose center is 1/2 and whose radius is 1/2 right there. Here is a challenge for you. Starting at this point, the point 0, 1, draw a line to the x-axis. I don't care where you draw, but if you draw a line from that point, which I am going to call, I'll call it N for the North Pole, N. If you draw a line from N to any point on the number line itself, you'll cut through that circle once and only once. And that means that every point on the circle has a matching point on the line. If I want to get to the point 0, I just go straight down. If I want to get to the point 1, I'll go through this spot. If I want to get to the point 3, I'll go, well, let's get to 2. It's a little easier to see. I'll go to this spot. Notice that that means that 1 is here and 2 is there. And if I go to do 3, it's there. And as I go further and further out this way, the numbers creep closer and closer to the North Pole. but they never actually get to the North Pole. If you take the limit as x goes to infinity, our points go to the North Pole. So you could say that if you want to treat infinity like a number, you should use the circle, and infinity is the North Pole. It's a, quote, normal number that way. This idea is called stereographic projection, and it's one of the ways we make good maps. Anyhow, there's your brain breaker for today. I can make infinity fit on a circle. More calculus questions. Chapter 4, section 1, section 2. Questions about the exam? Anything? Yeah, the one we just gave back. Yeah. Yes, ma'am.
Like, what if David Collins is asking about what's there?
Mhm.
You want us to write out the sheets that, what each part of it is?
Yes, because Rolle's theorem has 3 conditions. I should be able to show that all 3 are working, right? Just like in the mean value theorem problem, I was able to say, this is why I know this condition is true, this is why I know this condition is true, so I can draw this conclusion. When we do Rolle's theorem, I'd appreciate seeing the same thing. That's perfect. Yeah, so if you said, hey, I need it to be continuous, here's why I know it's continuous. I need it to be differentiable, here's why I know it's differentiable. I need the 2 ends to be the same, plug in, they're the same. On the advanced placement calculus exam, there's an instruction that explicitly says, if you are going to use a particular result, a theorem, you need to show that the hypotheses hold. And that's really what I'm trying to get you to do here as well. How do you know you're allowed to do that? Here are the reasons. More questions. For those of you with a passing interest in history, in addition to Rolle, there is a related theorem. In addition to the mean value theorem and Rolle's theorem, there's this guy Darboux. And Darboux came up with an interesting variation that allows me to relax the necessary conditions in the mean value theorem. The mean value theorem requires me to be differentiable, requires me to be continuous. I can weaken those conditions. Maybe I'm not differentiable across that whole interval. Maybe I'm not continuous across the whole interval. Darboux's theorem actually is related to this. I saw a lovely presentation on this last year at a professional seminar in the summer. I have no reason to leave your butts nailed to these chairs. If you don't have any more questions, I will see you tomorrow. If you still have questions, feel free to stay and ask them.
Thank you.
Thank you. You as well, Kate.